I will ask a few questions before the others. So I find this general idea of let's say arrangement of particles that you can use using your platform very convenient for many novel applications for which we have problems. And let's say I will cut this my questions in few parts. So the first would be the can you observe in the way experimentally phase transitions in between, for example, different lattice distribution that you can you switch easily from a cubic to a hexagonal, for example, or from any lattice that you like to another?
That's that's a good question. We haven't observed that experimentally. And the reason for this is, first of all, if you wanted to do something periodic, then you have to have the transducers placed in the right location. But then you could say, oh, let's assume that you have enough transducers to get these different lattices. Then say you have set the points in a particular lattice configuration and just switch immediately the transducers to another lattice configuration. Then maybe eventually they will all the particles will go to a new lattice configuration, but that doesn't happen in practice. You need to either go continuously from one to the other, okay? And we have ways. We're thinking of ways in which to do this, or you need to randomize the position of the particles if you want, insonicate the medium. And just and then put the particles back. So there's a step in the experiments that they do where they with my colleagues do, where they either, let's say, to make sure that the particles are evenly distributed in the fluid, they put some ultrasound transducer inside and they just create random waves that just put them in, distribute them evenly. Because these particles, if it's carbon nanotubes, they'll tend to stick together. If it's water and you put like carbon particles, they will tend to stick together. So you need to add some surfactant, some like soap, like dish soap or something like that, so that they disperse, and also like have them disperse by putting a bunch of sound in it. But I think that the continuous transition, that would be really nice, a really nice experiment to do. And we have ideas on how to do that. Because I mean, you can kind of see where I'm going to with this kind of approach, right? Because you have, if you want to translate something continuously, you can do it with this because it's just a set of unitary transformations, and you can just apply these unitary transformations continuously to take you from a configuration to another configuration. So yeah.
Okay. So the second question is, okay, here you distribute your particles, for example, in the fluid. Have you sent any additional signal to see, for example, let's say in the most stupid case, just to see if you can get a band gap, if you can get some.
That's I keep telling my yeah. So this is something I have. So you want to send another kind of waves to yes, verify that we're getting a crystal, right? Yeah.
For example.
Yes, and I have this is experiments that I have proposed to my colleagues, and maybe they will do eventually, but it's not me doing the experiment, so I cannot tell them to do this, but cannot force them to do this. But I think it's a really nice thing to do, especially, let's say you could combine this. Let's say you just do something simple, just like grating, something like that. Meaning, you could create a crystal with a polymer matrix and say metallic inclusions in it. Because we're working with ultrasound, this will give you particles that are about a millimeter away, or on the order of a millimeter away. And so imagine that if you put waves in there that are of about a millimeter, so millimeter waves, you will be able to observe this band gaps. Also, you have certain directions, preferred directions of diffraction and so on. So these are all experiments that will be really nice to do, actually. And actually to confirm that we have a quasi-crystal will be really nice. By the way, the nice thing about this is that you can do something that is of the order of, a few centimeters, you can do a cube that is about, we have experiments where we've done this with water at least, where you have a cube where you have particles periodically distributed inside. So that's a possibility. So, and I'm hoping that they will do it. So
you have to convince them, because in the alternative way, I mean, we have tried to design or to find out a way to get floating objects basically on the surface of the fluid, and then to study the surface gravity capillarity waves on this. So it's kind of free solids floating. It's like boats floating on the surface. But that, I believe that that's something you can design with this approach. It does not have to be fully in the volume, but let's say partially or let's say on the top of a fluid. And then in addition, you could send gravity capillarity waves. One of the main point of these waves is that the frequency that are involved are very low. And in that way, even the configuration of your crystal using acoustical wave can be extremely fast, because usually it's very hard to find to find something to study these time crystals. That's the main point where I want to come, because here I think you have a nice platform where you can make your configuration. You can change your, let's say, your phase inside. You can induce some motion inside of your fluid in a fast way, but only for, I mean, it's fast relative to gravity waves. It's not fast for acoustical waves. And I think there you could use this approach. For example, one of your slides in the beginning where you had this cubic array in the periodic arrangement. You had this, yes, this one, or the, yeah, for example, this one. So here you have this, on the right side, you have this, let's call it blue and red particles. I mean, this can be like ellipsoids, or like at the end assembly of your particles. But I mean, for topological effect, this is very important, very nice to have such configurations. And I think a very important aspect would be if you could come up with actually rotating them. You see what I mean? Individually, that they rotate. Of course, they would not rotate if they are just agglomerations of particles. They would have some reconfiguration. Some of these particles will move, but at the end, you get something that looks like a rotated particle.
You mean like each individual particle here being rotated?
Yes.
Oh wow, no, that's I don't know how to do that. It's actually something that with, I mean, my colleagues have been trying to do, taking particles that are not spherical particles but more like tube shaped, and then have them control the orientation of these particles. But we can do this for one particle. We haven't thought about doing it for many particles. And in this case, you see that the traps are kind of have a certain orientation to them, right? These are ellipses. They're not perfect little discs. So that's the orientation. If you have a particle that were oddly shaped, that's the orientation that it will take, but it will stay there. It will stay oriented in this way. I don't think I can rotate them at the same time, or I don't see how to do it, but I see how to use another kind of waves at the same time as we're making the experiment to study, scattering from this collection of particles, scattering from that other kind of waves, which is the capillary waves, right? To study, to show that this is also a crystal-like structure. And I should have said that also from the beginning, that this is not only for ultrasound. Any phenomenon that you can describe using plane waves that then interacts with particles, you can use this model to show that you get periodic or quasi-periodic patterns and so on. And so there is work out there where people are using lasers to place atoms and so on, and they've shown that you can put atoms in, you know, like this kind of pendulum-like tiling things.
Yeah,
So,
but some of these people in, let's say, optical tweezers, one of the key point is that the wavelength is extremely small compared to the objects that
yes, that's right.
It would be like having many transducers that you would have, and many of them would be just for one particle.
Yeah, but at the end of the day, you get if you get something that looks like this, if you get something that can be written as some quadratic function of the field, you can use the same tools that we have here. So if you can say my particles will tend, if you can express the locations where the particles will tend to go as some energy landscape, then you can use the same techniques.
Let me ask a last question. If you can just go back to this slide with the tilted ellipsoids.
Oh, yep.
Could one engineer like a domain wall? Let's say that I have two medias, one on the top, one on the bottom. On the top, they are tilted to the left. On the bottom, they are tilted to the right.
Yeah, I see where you're going, because you want to get the topological wave going through through both medium, right? So through the interface between the two media, right? Yeah, that would be really cool to do. I haven't thought about this, but I mean, you could imagine doing that after the fact. Let's say you fabricate this crystal, because you do it with a polymer, you harden the polymer, then you take that and you stick it to the same one, but oriented in a slightly different way.
Yeah, the point I was willing rather to hear that you could do it in real time in a fluid like.
Yeah, no, that would be better. Yeah, I agree with you, and we haven't thought of things where you have interfaces between two periodic media, but that sounds like something that will be fun to explore. So yeah, thanks for the suggestion. This is a really good suggestions. Yeah.
Okay, thank you. I'm just looking. Is there any question from the audience? Because I'm monopolizing the question time. No one is willing to ask. So in any case, thanks a lot for the talk. So your talk has been recorded and will be made available on the website, and I will be happy to further exchange with you regarding this possibility of basically tailoring or changing the properties of a crystal more or less in real time.
Yeah, that would be great. We'll keep thinking about it. Thank you, Marmer, for the really nice questions and for giving me the opportunity to talk here. And thank you everyone for coming as well and slugging through the whole thing.
Thanks a lot.
All right.